Thomson found the charge to mass ratio of an electron, and that's what ultimately gave him credit for the discovery of the electron. He didn't want the charge to mass ratio per se. He wanted the charge and the mass of the electron. But he couldn't find it. So enter Millikan. Robert Millikan, in the first part of the 20th century, performs an experiment that we call the oil drop experiment that is used to find not the charge to mass ratio, not to discover the electron, that's already been done, but rather to find the charge of the electron. And here's how it works. He's got two parallel plates. By the way, the diagram on the left is a little bit more detailed. I'm going to provide a little bit of a simplified diagram on the right, and this is what you really got to focus on, is this simplified diagram, because it's what's going to illustrate the basic principles behind this. We've got two parallel plates, and those plates are charged. The top plate in this case would be positive, the bottom plate would be negative, because the top plate is closest to the positive terminal of the power supply, and the bottom plate is closest to the negative terminal of the power supply. Now, we could have easily reversed that and made the top plate negative and the bottom plate positive, but we didn't. In this case, that's what it is. Now, we inject tiny little oil droplets in between these plates, tiny little charged oil droplets between these plates. We do that with something called an atomizer. An atomizer is basically like a perfume dispenser or a cologne dispenser. You go to a store, you buy some cologne or you buy some perfume, and you spray it, and the liquid, the thing that was a liquid just like water, turns into this fine mist. It atomizes the perfume or the cologne. Now, that doesn't mean that it's literally turning the perfume particles into the size of atoms. It's not. Okay, nowhere close to that scale. But it's making these particles really, really small. That's what we're doing here. We're making the particles of oil really, really small when we inject them into these plates. Now, some of these particles will be charged positive, or some of them will be charged negative. Some of them won't be. Sometimes we have to actually irradiate them with X-rays in order to cause them to become charged. How they become charged isn't really important for us. Okay, we just have to assume that they're charged. Whether we had to irradiate them with X-rays or whatever, they're charged. Some positive, some negative. What I want to do now is focus on one of these oil droplets at a time. If I was Millikan, I would be looking at one of these oil droplets through a microscope. They're that small that you have to look through a microscope to see them. I would be looking at one single oil drop through a microscope and analyzing the motion or lack thereof of that particle. Let's look at the forces acting firstly on the negative particle right here. What two forces would act on this negative oil drop? What's one? Good, the electric force. The electric field is downward here. The electric force on a negative particle is always what? Opposite to the field. So the electric force in this case would be upwards. What other force acts? Yep. Good, gravity. Why do we pay attention to gravity now when we didn't pay attention to gravity with the cathode ray tube? Yes, way bigger, right? The mass of an electron was so small it didn't matter with the cathode ray tube. Now we're not talking about electrons, we're talking about oil drops. Small oil drops, but still much, much, much more massive than individual electrons. So we do have to pay attention to the gravitational force. Okay, there's the basic free body diagram of the first oil drop. Let's take a look at the positive one now. We still have an electric force acting on this way. This one. Which way does the electric force act on the positive? Up or down? Yep. Down. Are you sure? Positive, the force is with the field. The field is downward, the electric force has to be downward as well. The gravitational force is going to be downward as well. We're going to analyze both of these particles. First, this one. We may find that one force is bigger than the other. If that's the case, this charged particle accelerates. But if those two forces balance each other, this charged particle, this oil drop, will either be suspended or it'll go up or down at a constant speed. That's what I want to look at first. When the charged oil drop is either suspended or traveling up or down at a constant speed, but not accelerating. For those oil drops, we would say Fe equals Fg. We would say, you guys remember the equation for Fe? For electric force, not electric energy, but electric force. Yep, QE, good. Q times the electric field. And that's equal to, of course, M times G. Now, sometimes we have to replace E with delta V over delta D. Sometimes we don't. Depends on the givens that you have in the question. Rearrange this equation. Solve for Q. If we had numbers and subbed them in there and solved for Q, we would have solved for Q the charge of what? Have we just found the charge of the electron? No, we haven't. What have we found the charge of? Yep, the charge of an oil drop. Yeah, we found the charge of a single oil drop. The charge of that oil drop might be 3.2 times 10 to the minus 18 coulombs. When we repeat the experiment, analyze a different oil drop that is suspended using the same analysis. We find that charge, and maybe it ends up being 4.8 times 10 to the minus 17 coulombs. I do it again. Maybe we find that it's 1.6 times 10 to the minus 19 coulombs. Do it again. Maybe we find that it's 9.6 times 10 to the minus 18 coulombs. So on and so on and so on. Do it 100 times. Do it a couple hundred times. This is what Millikan found. He found that all of these oil droplets had a charge of either 1.6 times 10 to the minus 19 coulombs or a multiple of 1.6 times 10 to the minus 19 coulombs. So he said, he concluded that there is what we call an elementary charge. An elementary charge. We used that word before, right? We used that term. We were finding the charge on our data sheet of an electron. Now we know what it is. The elementary charge, the smallest possible charge that you can have, the elementary charge, which also, by the way, corresponded to the charge of an electron. And its value, of course, is 1.60 times 10 to the minus 19 coulombs. So we concluded two things. One, there's an elementary charge, the charge of an electron, 1.6 times 10 to the minus 19. The second thing he concluded is that charge is quantized. And what do we mean by that? Well, let me tell you this. In Canada, our money is quantized. We don't have pennies. The smallest we have is nickels. The nickel would be the elementary coin. Doesn't get any smaller than that, right? The nickel is the elementary coin, and coins are quantized. In other words, you can have 35 cents, 7 times a nickel. You can have $1, 20 times a nickel. You can have 10 cents, 2 times a nickel, or 5 cents, 1 times a nickel. But you can't have 7 cents. You can't have 23 cents in Canada. It always gets rounded. So you can have a whole number multiple of the elementary coin, but you can't have anything in between. Okay, that's what quantized means. Quantized here means that you can have 1.6 times 10 to the minus 19, or you can have 300 of the elementary charge, or you can have 20 of the elementary charge, or you can have 60 of the elementary charge, but you can't have 20.8 elementary charges. You can only have whole number multiples of that 1.6 value. Let's do an example. It's example number 1 in the booklet that you have. It says a Millikan-like oil drop experiment is performed with an oil drop that has this mass. Here's the electric field. Top plate's positive, bottom plate's negative. What's the number of the electrons gained or lost by the oil drop if it's to be suspended? What's the key word here? Or one of the keywords at least, Rachel? Good. Suspended. If it's suspended, we know that Fe will be equal to Fg, or at least the magnitudes will be equal to each other. Qe is equal to m times g. And we're looking for the number of electrons. Don't worry about that right now. Just solve for Q. Okay, we sub our values in there. We get 4.89 times 10 to the negative 14 times 9.81 divided by E, which is 5 times 10 to the 5. Is this a charge of, what, 9.59 times 10 to the negative 19 coulombs. Okay, there's my charge. We want to find the number of the electrons, though. How do you find a number of the electrons? Yeah. The number of electrons is the total charge, 9.59 times 10 to the minus 19, divided by the charge of one electron. And that's going to give me, I think it's 6, isn't it? Yeah. 6 electrons. Gained or lost? Ooh. Gained or lost? In other words, is this oil drop negative? If the electrons have been gained, the oil drop is negative. If the electrons have been lost, it becomes positive. Go ahead. How come? Okay, good. Let's draw a picture, because a lot of people probably didn't really understand your train of thought there. Let's draw a picture. It's always good to draw a picture with these. The top plate is positive. The bottom plate is negative. That means that the electric field is downward. Agree? Positive toward the negative. In these diagrams, there's 3 things you want to do. One is the electric field. Sometimes you've got it, like we have here. Sometimes you've got to find it. If we have it, draw it. The second thing you want to put in is the direction of the electric force. This is suspended. If this is suspended, gravity acts down and the electric force would act up. Okay, the electric force acts up. Gravity, of course, always acts down. Okay, now what's the type of charge? If the force is up and the field is down, this must be a negative charge. So there's the third thing. It's always the 3 things in green. You'll have 2, you're going to find the third. In this case, we had field, we had force, find the type of charge it is. If it's negative, then that must mean that it was 6 electrons gained. If it was positive, it would mean 6 electrons lost. Another question, maybe you got the type of charge and you have to find the direction of the field or something else. Yep?
When we were drawing the diagrams for the round experiment, you said that it just goes top positive on top and negative on bottom.
Yep.
If we were given a question like this on the test, would it have to clarify?
No, it would have to be clarified, yeah. No, you wouldn't assume that if you're given a question like this on a test, yeah, it would have to be clarified. Usually it's in a picture, but it would have to be clarified because you could absolutely get something like this. Absolutely. It reverses things, right? In this case, the negative particle is suspended. In that case, the only way to suspend it would be if you had a positive particle. Okay. All right. Take a look at the first 3 questions, please, on worksheet number 23. Questions 1 to 3 on worksheet number 23. Okay, let's have a look at number 2. It says an oil drop has this mass. It's suspended. Again, that's the key word here. It's suspended. That means our forces are going to balance out here. Fe equals Fg, not Fe equals Fm. That would be the velocity selection chamber of the cathode ray tube. This is the oil drop experiment. Fe equals Fm. Qe equals m times g. We want to find the number of the electrons. But let's find charge first, mg over E. But we have to find E first. Anybody know how we're going to find E? Oh, no, sorry, we do have that. 2.2 times 10 to the 4. So listen, we sub our numbers in here. We got M, we got G, we got E. We solve for that. And that's going to work out to be 3.21 times 10 to the negative 19. Good. How do you find the number of the electrons? The number? Yeah. Yeah. Divided by the charge of 1. The number of electrons is 3.21 times 10 to the minus 19 coulombs divided by 1.60 times 10 to the minus 19 coulombs. That's going to give me two electrons, 2 excess electrons. We don't have to worry about a diagram in this case because they're not asking me for the type of charge, negative or positive. They're not asking me for the direction of the force. They're not asking me for the direction of the field. So you draw it if you want, but it's not necessary here. Remember, it's those 3 variables, the force, the field, and the type of charge. One of those things you need to find, you need to draw the picture. Okay, I am going to show you one more little thing with this before we call it a day here. We want to know now what happens for these charged particles that are accelerating. That could be a particle like this. It has an electric force down and a gravitational force down. That's going to accelerate. Or it could be a particle like this, where FE is up and FG is down, but FE is smaller than FG. Or it could be a particle like this, where FE is bigger than FG. Bottom line is, we have an oil drop that's not suspended or traveling at a constant speed. Rather, it's accelerating. What did you do in physics 20 when you had a free body diagram with 2 forces acting? Remember that? We did it also earlier in the context of electricity where we had 3 charges in a row. When we have 2 forces acting on one object, we say, yep, F net is equal to the sum of the forces Fe, in this case, plus Fg. We replace F net with, at least usually we replace F net with, what is it? No. No, if it was 0, it would be suspended or traveling at a constant speed, right? We're going to replace F net with M times A. QE plus mg. Got it? This term, this is always going to be negative. Now you got to pay attention to that. Okay, when you sub numbers in, you got to sub numbers in positive or negative. Fg will always be negative because it's always acting down. The electric force, QE, well, that could be positive or negative. And you're going to determine that by a picture. Remember we said draw that picture? You determine whether the electric force is up or down based on a picture. And the acceleration will be positive or negative. And usually you're told whether it's accelerating up or accelerating down. Sub your numbers in with positives and negatives this time. Solve for Q. And then do the same thing, same kind of analysis you did with the suspended particles or the constant velocity particles. They're all going to be 1.6 or they're all going to be multiples of 1.6 times 10 to the minus 9. One more example here. This is involving an accelerating charge here. An oil drop with this mass accelerates downward at a rate of 3.2. What's the charge on the oil drop if the distance between the plates is 11 millimeters and the potential difference is 833 volts? It accelerates downward. Okay, if it accelerates downward, this is an F net problem, right? F net is equal to Fe plus Fg. We only set Fe equal to Fg when it's suspended or traveling at a constant speed. Now let's replace F net with M times A, QE plus M times G. Let's start subbing some numbers in here. My mass is 5.50 times 10 to the negative 15. My acceleration is, anyone? Negative 3.2 because it's accelerating downward. Just 3.2, I guess. Q, that's what we're looking for. E, we got to find E. Okay, let's find E now. Delta V over delta D. 833 divided by 11 times 10 to the minus 3, 11 millimeters. That gives us a field strength of 75727.27 volts per meter. The mass is 5.5 times 9.81. Okay, what about the right-hand side? We established that that's a negative acceleration. What about gravity? Positive or negative? It's negative. Let's take a negative in front. I don't care whether it goes in front of the 9.81 or in front of the mass, doesn't matter. What about the electric force? Positive or negative? As soon as we start subbing numbers in, we got to worry about that, right? Is it positive or negative? Draw a picture. Draw a picture. Here's the charge. Here's the charge. Gravity acts down. It's accelerating downward at 3.2. If it was just gravity, what would the rate of acceleration be downward? 9.81. So there must be a force up to counter that, right? But it must be a force smaller than gravity, because if it was bigger than gravity, what would happen? It would accelerate up. So it's accelerating down, but less than 9.81. Okay, the electric force must be up. So we're going to leave this as a positive right here. Okay, get this number. Get this number. The negative, take it over to the other side by adding. Divide by 75727. And when we do, we end up getting a value of Q 4.80 times 10 to the minus 19 coulombs. Now, we want to know the charge. I should have told you at the beginning that the electric field is downward. You needed to know that to determine the type of charge you have. I got 4.8. That doesn't tell me it's positive. That just gives me the magnitude. Hold on one second here. If the field is downward, go back to the picture. If the field is downward and the electric force is upward, then what type of particle do you have? What is it? It's a negative particle, yeah. Not an electron, but a negative particle. The force is opposite to the field. So we're going to say negative 4.8 times 10 to the minus 19. Here's your homework for tonight, guys. You saw earlier, practice question set, number 27 went up. Probably saw a notification for that. That's on the cathode ray tube. In addition, I want you to do worksheet number 23, questions 1 to 4. You've already got probably 3 of those questions done.